that depending on how fast you tear, the resistance is different. And we talked about, I talked about the desire to indicate, at least in that zero speed limit, how you want to model it. But I think I should try to finish the discussion about this, generally this rate and temperature dependence, and give you the conclusion about it. So let me try to do that by really reminding you that we have in the literature for nearly 70 years, either the nominal so-called tensile strength or the so-called tear strength, which is the same as it's all inspired by Griffith's energy release rate anyway. In either case, this would be to tear with certain speed. This would be to stretch with certain rate. That could be just how fast you are changing your length relative to your initial length. You would have curves like that in each case. I'm not going to draw many because there are many, you saw them. And I just want to emphasize the point now. And in either case, we make a shift according to WF, so such that you actually started to plot lambda dot times the WF shift vector. So when you do that, your intention is to show that this thing now collapses here. Okay? I just want to point out, at least in one case, why I have said this amounts to thinking about a viscous process. So let's take, as I said, I had this neatly drawn on PowerPoint, but it didn't get uploaded. So let's take a case, what I call it elastic stretching limit. So by that, if you still remember your dear rheology, elastic stretching is a limit where the stress response is not rate dependent, meaning, for example, you don't pick up any entanglement. So let me remind you that it means if I stretch slowly, I will break there. If I stretch a little faster, I'll break there. If I stretch a little faster yet, I would break there. Same can be said about temperature. So this 3 points could be your 3 rates, or could be your 3 temperatures. Can anyone tell me? Sorry, the lambda dot. Sorry, I'm get confused now. This is lambda dot. This is, look at the typo here. This is just a raw data that I complain people typically do not provide. So these are 3 different stretch rates, or it could be the same rate stretched at 3 different temperatures. Can you tell me, in the case of temperature, 3 is a high temperature or low temperature? Yes. Because we keep saying the material was more stretchable at lower temperature. That's what this is. But the fact these stress strain curves overlap means there's no rate response. Means, do you understand? That means it's purely elastic. Yeah, because you don't need to be in a hurry. Meaning, no matter what temperature and what rate you are performing your experiment, you hit the same stress. Except the breaking is not at the same time, but you hit the same stress up to the point where the first one break, which means there's no viscoelasticity. Do you understand that? Meaning it's a purely elastic system. Please don't bring Maxwell because it's purely elastic. If you like to use Maxwell, don't put a dashpot there. Call it the hook element, which is what it is. The key point here, by the way, you should also know what is instead of hook element, what is a Newtonian element? It's that. Do you know that in either of these two limiting cases, there's no such a thing as a relaxation time? In the solid case, sometimes I say, oh, your relaxation time is infinite because solid doesn't do. In the liquid case, I typically say the relaxation time is 0 because it's always instantly responding. However, when you want to say it, there's no tau. There's no relaxation time. Yet, so let's consider that limit. In that limit, I promise you this still occurs. For example, this 3 points, the last one is here. If it's a rate, it would mean my 3 points here, right? If it's a temperature, it would have meant, in that sense, I should add a third line. If it's a temperature, I would be saying that I'm looking at one rate, I got 3 temperature. Give me 3 different points, right? Are you with me? This 3 point could be the 3 temperature, which would be my vertical reading of this 3 points, right? If I'm looking at a single temperature, then of course I'm just looking these 3 lines with being the 3 points. Yeah. I know. I'm counting on you to, for my economical reason, that plot of 1, 2, 3 could either be 3 temperatures or 3 rates. In the case of 3 rates, could be pretend this is 1 temperature, T1, this is T2, this is T3. And they are, of course, in the relationship of that. Yeah? So I just quizzed you that if this 3 point means temperature, it would be the third temperature being 3 would be the lowest one, right? Lowest temperature. Did I make it too complicated? I know this is it's complicated only because I'm trying to be economical. That this is the same thing. So let's look at what it means. Oops, what did I do? Oh, it's because what it means for you to have been doing a WLF shift. Recall what WF means. I'm really hammering on it now. TA in our 1995 sense polymer physics due to WIF, F being Ferry, who is the leading person in rheology in that, for that contribution. And it is discovered that this WF works and it represents the ratio of relaxation time that you all did for that of this type. But I just told you there's no relaxation time. Yeah. At a given temperature, right? Higher rate at a given temperature. Either way. in which case that's why I invite you to look at it vertically. At a given rate, stretch at 3 different temperatures. Or one temperature stretching at 3 different rates. So it's all covered in the 3 lines here. So now we did WF, which is what the literature has been doing. Meaning we're invoking this WF shifting factor. I just try to remind you the way we learned about WF is that this shifting factor is a ratio of relaxation times. Here, as I just said, it's a purely elastic stretching limit. There's no relaxation time. So you are being pushed back to suggest what then? There's still something that's temperature dependent. And even though you can no longer define relaxation time, you know, in fact, you know why you are not picking up any rate dependence. For example, the relaxation is too fast. The relaxation time exists except you are not accessing it. It's too fast, for example. And what determines the relaxation time? Classically, it's the so-called segmental friction coefficient. If you recall the bead spring model, that's how we perceived where the temperature dependence of relaxation time comes from. So you would be pushed back to suggest, oh, there is such a thing that will change with temperature. That it would be the friction, monomeric friction. And this shift, in both cases, really amounts to suggesting that your tensile strength is now a function of the shifting factor times a stretching rate, or call it the G. Basically, it's a function, the propagating velocity times friction coefficient in this case. In other words, now I can formally convincing myself what I speak about is purely something viscous. In other words, I'm repeating what I have said before now, that this shift, if it is to be accepted, you are really implying that your material is being dictated by this product of friction coefficient times so-called deformation rate. And this is indeed purely viscous in origin, this quantity, completely viscous in origin. I want to say that gamma dot times tau is not necessarily a viscous quantity, but this is. Okay, so I think I don't want to delay any final answer to this. Meaning, I simply want to offer I'm being pushed to a corner. I cannot accept the idea that this WF really has its meaning, that your quantity depends on this viscous. It's really viscous. It's proportional to viscous stress. And there's no viscous stress here. So this is a true contradiction, internal contradiction. On one side, you have no internal stress. On the other side, you insist the internal stress, the viscous stress is operating to allow you to think about this shift. So there are just 2 points to make now. One is, if it's not relaxation time, if it's not polymer relaxation time, what is it? Because I just try to convince you in this elastic stretching limit, there isn't any relaxation time that you're looking for. It's this internal time scale that is measuring how fast you are stretching. This goes back to the familiarity of rheology. Rheology is all about some internal time scale relative to external rate of deformation. And that internal time in rheology is indeed the relaxation time. And I just forced myself to realize that there is no relaxation time. At best, I can force myself to think there's some viscous quantity, which makes no sense because there's nothing viscous here. Okay? So obviously, you need to look for another way to think about what is that internal relaxation time. In other words, to explain what is that internal clock. So let me just quickly give you the final answer. Let's again think about why this shift appeared to be successful. In other words, it certainly has the trend. If you just shift horizontally, you tend to converge. All the data seem to have a master curve-like. So let's just examine the meaning of this. The meaning of this 2 points, okay? Just this 2 points, of course, come from what? From 2 different temperatures. It's a horizontal line I'm looking at. Either point achieve the same level of stretching, right? Horizontally. Right? Are you with me? Either one of them show the same tensile strength. According to this, showing the same level of stretching. What's different? The difference is at this higher temperature, I had to stretch a little more. At this lower temperature, I was able to afford to stretch less, slower. Apologize, right? Faster versus slower. So what's the interpretation? The interpretation is at the lower temperature, your network is longer lived. So you can afford to spend more time reaching that point of comparable tension. Right? So this was all we did it some long time ago when we speak about the once you have a energy barrier for dissociation of your covalent bond, you realize that your lifetime is longer at a lower temperature. So lastly, let me explain why this. So this is perhaps a fascinating place to see why you have this. Everything same to work if you use WF. Why? It's because your so-called WF shift, which is nothing but trying to capture the temporary dependence of your relaxation time, in fact. Both of them says your time scale is longer at a lower temperature. So if you want to make a plot, let's say you do it as 1/T, then this relaxation time basically says the colder the temperature, the longer the relaxation time is. Whereas WF typically will do something similarly. Okay. So this is your polymer relaxation time according to WF. They both have the general trend as you cool. If I plot it as 1 over T, the colder temperature is to the right. So as you go to lower temperature, the time grows. For the bond breaking as well as for your polymer relaxation. The discrepancy, as I try to draw between them, is the discrepancy of not perfectly able to produce a master curve. But the discrepancy may or may not be very large between them. So it's so amazing, right? You can have something approximately capturing everything, but completely different physics. Completely different physics. Are you with me on this? Both have the tendency to be more slug, to involve longer time scales as you go to lower temperature. So this is captured because it's always relative some reference temperature. So this is captured by AT, and this is the black line is the bond lifetime, and I usually choose a symbol of gamma T. Same thing, T relative to reference, such that I can reference it in a way that this is all at 1. So relative to this low temperature, normalizing the reference temperature. In other words, the reference temperature is this lowest one. Then you got a factor of gamma versus AT, and they are not identical. They can be quite similar. So a lot of current research in our group is to delineate the difference between them. So please, at this point, if you are just trying to say, I want to be just qualitatively correct, then you can forget about my theory. But it's not a so amusing. This qualitatively correctness is precisely what's wrong, because they are qualitatively different. I'm trying to play English words now. Jesus Christ, it's qualitatively correct, but it's precisely qualitatively incorrect. You get it? I sometimes just find the language so amusing here. These two represent fundamentally different physics. Pick and choose. So I probably should mention one point. I think, given time, I could talk more. So since we are reaching the last lecture, I do want to mention about one of the most important experiment before we go on to the Lake Thomas model that I promised to show you. The most important point is this one. It's all, I once said it, let me write it down. It's all small world. It's all a small world because Beakey was a famous professor at University of Akron in the 60s. I want to hammer on this point, and it's because of his theory that people just agreed, let's just have WF shift. Don't bother finding an alternative internal clock. So you heard enough about viscoelasticity, or I would try to tell you that textbook saying this elastomeric fracture is all a viscoelastic process. What they really mean is whenever you speak about viscoelasticity, you necessarily speak about a clock. And they thought this clock was polymer relaxation time. And you can blame Professor Beakey for it. And let me further verify how this is improper and incorrect. You could imagine, perhaps, that indeed this whole fracture thing is polymer relaxation time related, as according to Beakey, who I have in various places discussed about why he was misled to make that conclusion. But I'm running out of time. I don't have time here to discuss it. But let's just take one step. For example, take what step? Take the step that, for example, at what was it? If you try to, let's do it. I don't need to complicate it. If you try to use lower temperature, you find okay. So let me see if there's a better way to do it. There's so many parts to it. Try to see if I can simplify it. But basically, let me give you a simple way to visualize it. For example, if you have a notched sample and you so-called load it up to stretch to a certain level, now you start to see that the crack will start to propagate. You will find basically at a higher temperature, the crack will propagate faster. Okay, so let me try to make sure you understand. I'm going to stretch to a certain level, I hold it, and I find my crack start to propagate. You'll find at higher temperature, the crack will propagate faster. It says, okay, I surely understand that. At a higher temperature, your relaxation time is faster, which permits this, when the next chain breaks, the stress has to pass to the next chain, and it will be easier if your relaxation time is faster now. So it all seems to, it's all over the place, but this seems to be a way to invite the WF back. By the way, what is the alternative? The alternative is at higher temperature, it propagates faster because at higher temperature, the lifetime of the bonds, the lifetime of the network is smaller. Okay? So it's right. It's just for your. I say this because. So basically, this of course also explains because at the higher temperature, your lifetime is shorter. Therefore, you will propagate faster. And I have no way of differentiating between the two. Seems to me, from this angle. Right? I'm stuck. But the thing is, people have done all there is to do, and this is one of the most brilliant experiments. So it turns out Smith and his co-worker Stedry had a paper in 1960, and they did the most clever thing there is. That is, you basically take a piece of sample, you stretch it, and you stretch it to the same level at different temperatures. And I mentioned this once before. And wait and see if it breaks. Lo and behold, they do. So if you plot that, you can call that delayed rupture time as a function of 1 over t. So why this is a beautiful experiment? You stretch without a cut either. You stretch and hold. All the relaxation is gone. Nothing is moving, and you just wait. There's no way you can invoke any viscoelasticity in the problem. The chain already happily adjusted to whatever level of stretching that you did and sit there. And you wait. At the colder temperature, you wait longer. This is an experiment that went as long as 1 week of waiting. Very patient experiment. What do you see? On semi-log scale. How on earth you explain this? I actually, no matter how I try, I don't know how to explain it without using my theory. How you explain that you sit there, same temperature, a colder temperature, wait longer, for what? Waiting for what? When it breaks suddenly, like a snap. So obviously, it's not a place for us to worry about the crack propagation speed or anything. It simply just catastrophically ruptures. Since by that time, 1960, we are quite familiar with what's going on. And of course, the author fits this through the WF. Shift factor, that's the black. Approximately, it qualitatively, I joke with you again, it qualitatively captures everything. Other than the fact I don't know why it captures it. People call that viscoelasticity, I heard. Well, yeah? This is several different temperatures, too. 5 temperatures, 1 over T. So this induction time, the waiting time, is measured at 1 temperature, and then I go to another temperature and measure the same induction time, meaning I stretch to the same level, T1, T2, T3, Tn. It's all involving the same amount of stretching. Oh, hold on, you're probably got that 5 crosses are 5 data points from induction time measurement. Okay? So it reveals that whatever this magic induction time is a function of temperature. Let me try, so let me try that WF temperature dependence. In fact, you can always normalize, right? You can always normalize this induction time by the coldest temperatures one, and so you can set up. I think the confusion that probably Caroline had is I'm not specifying. See, this is the power of certainly the power of log scales. I don't know how long I have to, I have to spend some time teaching you how powerful log scale is. Imagine your vertical axis are, let's say, 4 or 5 decades, okay? It's, in this case, in the unit of second, okay? The longest one was 1 week, all right? I can blindly plot my WF in the same temperature range in an arbitrary way, such that, in other words, remember, I'm the one always teaching you guys everything has unit, you better not mess up. Here's the case, because WF is dimensionless, yeah? I think you're confused exactly because of that. WFA is a dimensionless quantity. It's the ratio of 2 relaxation times. So you're saying it's outrageous. On one side, you have second here. On the other side, you said you don't care what that is. I really don't. In other words, let's say this is, just make it up. So this is 10 to the 6 second, and here is, let's say, 1 second. Huh? Fair? I can close my eyes and not worry about this is second, and still bring my WF into the same range of 1 to 10 to the 6. No, that's where the issue is. The 5 red crossing as a data point. Indeed, no shift is involved. They are just different relaxation times. Different induction time for the breaking. Right. So how do I put it for you? Let's see. They did do the shift. I just don't recall how they are doing it in the sense of when we have a break, I can find that paper and show you guys what happens. But at the end of the day, what you recognize is there is an internal clock that's dictating how long it takes to break. And this internal clock is a function of temperature. And that's this red 5 points. At the end of the day, the only way that makes sense is to tell me, is to say, oh, by the way, I know what that internal time scale is. It's my polymer relaxation time given by WF. To check whether I'm right or not, I plot my WF on top of this curve. In the way I don't, do you understand? In the way we don't care about units. It turns out the WF in this range will also change by a factor of, let's say, of 6 orders. And I can just arbitrarily shift my WF to the region and see if they match. Oh, better yet, you can always just normalize it. If you can always, just like what I did earlier, call this one the reference point. In fact, this is a point I want to make, actually. Call this the reference point, then, of course, that's exactly WF equals 1 point, right? That's the coldest temperature. The rest is all, look. If this is the coldest temperature, the rest is all warmer, therefore it's all smaller than 1, right? So it's coming down. And you have no trouble normalizing your experimental data with the coldest one, right? Just divide by the coldest one first. In fact, this is the amusing point I'm making. Look, this looks quite okay. Let me tell you what is not okay. If you normalize it, I'm just writing this curve in parallel, right? I'm trying to amuse you, actually. Since you asked, I take advantage of that. Look, which way you think is better revealing the separation, the difference between them? Passing through the data or the dashed line? Did I confuse you with that question? Do you get it? Oh, Lord. In our original paper, indeed, red is the data, black is what they draw, because they try to fit through the entire data range. I replotted by normalizing them all to 1 for the coldest one, and then, which necessarily implies the black one become the dashed green one. They are just vertically shifted. Which one shows the difference better between the data? Of course. To me, that was actually quite revealing. I said, oh my goodness. It's quite systematic. It's not, you see, when you fit through it, you can blame this is just experimental uncertainties. When you normalize, you see this is systematically deviating. Okay, actually, let's take a quick break right now.